And welcome to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman, and we are going to continue our series of linear algebra tutorial videos by looking at section 1.5, which covers matrix equations. This should be probably a little bit shorter than what we've been dealing with before. But it does kind of carry over what we've already looked at in a pretty useful way that is going to matter a lot going forward. So let us look at what the matrix form is. Now, say we have a system of equations, linear equations, I should say, like this. Now, this is back in the early days of 1.1 where we were looking at systems of linear equations, and since then we have already looked at putting it into like an augmented form, which, if we were doing that, just to refresh your memory, that would look something like having a coefficient matrix on one side. Here, for this example, it would look like this. And then dividing it with a line and having the solutions on the right side, right? This would be augmented. But it turns out there's actually a more concise way of doing this so that it is all matrices, and it will actually help us solve it in a different way. So let's break this up, right? So if we look at this, we see a few different components of information, right? One of them is going to be things like, things like the actual coefficients, right? Another piece is the solutions, obviously, but there's also a third piece, which are the variables themselves, right? So these x's and y's and z's. So we're going to basically pull those apart and reassign them to their own special matrices, right? So we're going to let A be the coefficient matrix. I'll draw that in green so you see exactly like what I'm pulling from this. So this guy I'm going to write out as the coefficients, just like it would be the left-hand side of an augmented matrix, right? Now, X is going to be our variable matrix, right? So in this case, that is going to look very simple, just X, Y, Z. If all of these were X1s, X2s, X3s, that's what we would write, but in this case, it's just X, Y, Z. And then finally, B is going to be the solutions. Now, if we think of this as like what's actually going on in this system, right? Basically, what we're doing is we are multiplying A times X, right? And the solution we're getting is B. So that is actually going to be our general form of matrix equations. Just AX equals B, right? Now, an interesting thing that we can note about this, and a very simple proof, is relating to inverse matrices, which we just covered in our last video. So if you're a little bit rusty, I recommend you take a look at that. So if A inverse exists, well, we already said that AX equals B, right? Well, simple algebra says that what we can do, if we add something to both sides of this equation, it's not going to change the equation, right? So I'm going to multiply both sides by A inverse. For consistency, I will put the parentheses around the B, right? Now, we remember from last time that A inverse times A just equals the identity, right? Which is just equal to 1. It's practically trivial. So we can simplify this by just saying x is equal to A inverse B. And this turns out to actually be pretty important, because what this tells us is that if we have the inverse of A and we have B, then we can find the solution to the system. And that is almost a little less efficient than some things we've done in the past, strictly because it requires that we find A inverse first. However, it is still going to be a pretty useful tool, and instructors generally want you to be able to know it, so I suggest that you practice a little bit with this. Before we get into examples, though, I do want to look at something called a homogeneous linear system. So systems like this are going to be sort of the same form of the AX equals B, but in this case, just B equals 0, right? That's pretty much all this is saying. And this might seem like it's trivial, right? But it is kind of worth noting a couple interesting aspects of this. So the first thing is that since AX equals 0, these are always consistent. Right? They're always going to have at least one solution, right? Every time. And how do we know this? Well, A times 0 is 0, right? That is a solution. This is always true. And this is what's called the trivial solution. Little buzzword for you. It'll come back up later. So at this point, if we know that there's always one solution, right? The question is no longer, is there a solution? The question, if I can spell, which clearly I can't, the question is now, is there only one solution? In other words, or are there infinite? Right? So a little bit different of a plan of attack here. But essentially we are still kind of looking for an answer. And in order to find this answer, it's going to look a lot like what we did to find the inverse of a matrix, right? Basically the idea is, well, if we have AX equals 0, right? And X equals B times A inverse, we can kind of look at that by saying, well, if we just append the 0 vector to A, then we can row reduce this, right? So let me write that out. And when I say 0 vector, it's just going to be, I'll do this in green so it's clear that this is a sidebar. Just one single column of all zeros, however many that you need, however big A is. Bring to row reduced echelon form, RREF, because I'm lazy. Okay, so from here, once we do that, we can write the solution in a vector form. And that, in general, is just going to look like x equals number, right? It's just a vector. So this is going to be pretty clear when there is only one solution. But if there's infinite solutions, the way that we write the vectors are a little bit different. You'll remember in past videos when we talked about like what free parameters are and infinite solutions, there are times that there could be more than one free parameter, right? Like if there's two columns without a pivot, for example, that means that there are going to be two variables that do not depend on anything else. So when we have that, say, just for example's sake, say that we have like an x1 equals 2t minus 4s because x2 equals t and because x3 equals s, right? This is going to be an example of like once we've already solved this, we managed to get two different variables in place, right? Well, if our vector that we're trying to solve looks something like x equals x1, x2, x3 in a vector form, well, ordinarily, if we just want to write that out as is, we could do that, right? By just kind of saying like in x1 place we have 2t minus 4s, in x2 place we have t, in x3 place we have s. This is valid, but the thing that at least I'm noticing about this subject is that we like a very clean solution, right? Something that kind of pulls out all of the factors of anything and just leaves it nice and crisp. We can make that happen with this, right? By seeing that this is essentially equivalent to factoring out the variables and adding the two together, right? So we could say t times, so we can kind of split this, right? So t times 2, 1, 0 on the last one because the x3 does not have any t components, plus s times the vector -4, 0, and a 1, right? And if this looks like really obscure, like how the heck did we get all of this? You can absolutely just like work backwards and find it, right? Because we've already noted like how to do a scalar, right? So basically that first vector would turn into 2t, t, and 0. And then we would add that to the second vector, which would turn into a -4s, 0, and s, right? Which, when you add those together, is going to give us 2t minus 4s, t, and s, which is exactly what we started with, right? So that is kind of like a clean way to write it, and if you do end up with a problem like this, they're going to probably want you to bring it to that cleanest form. So it's really good practice to just kind of start viewing things like that. And the interesting part about this too is that this right here, this represents all possible solutions to the linear system. We have found them all and laid them out so nicely. Now we can show off our work with pride. Now, since we related the matrix equations earlier to inverse, I want to just take a second to do that right now. So, once again, if A inverse exists, then just to reiterate, we can solve this the same way that we did before, right? Except it's a little more trivial now. So if I have ax equals 0, and I multiply both sides by A inverse, well, this is just going to be 1. You pull down the x, and this is just going to be 0. So what did we get? We got x equals 0. Pretty cool, huh? All right. So let's just take a minute and look at kind of a brief example. And this will be kind of a shorter example, but it will take us pretty much from start to finish. So it's probably pretty good to see. So usually you're going to be not given like a x and b, but just like the system itself, and you need to parse those out, right? So, excuse me. So how do we do that based on this? Well, I can look at this and we see the variables are x, y, and z. So if it helps to start with that one, we automatically know that the x vector is x, y, z. Another super easy one to see is going to be b, right? So b is the solutions. So in this case, -1, 1, and 1. And all of that which is left over is going to be a, right? It's going to be a coefficient matrix. So I'm just going to go right across. It's going to be -1, 0, and -1, and so on and so forth. Hopefully by now you're pretty comfortable reading these off, but if not, just practice, 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 and you will get there, I promise. Okay, so the directions tell us that we need to solve using an inverse matrix, right? So the first step is we need an inverse matrix, right? So we're going to start by solving for A inverse. And if you don't know how to do this, I refer you to our most recent video on section 1.4, which goes over the inverse of square matrices. But as a refresher, we're going to take the matrix A and append a 3 by 3 identity matrix, since A is 3 by 3. And then we're just going to bring this down to reduced row echelon form. The first step I'm going to take, and this may not be what you would do, but I like to get everything very clear. So I'm going to interchange the first and third rows, because the third row starts with a +1 pivot. And make sure when you do any row operations, you are doing it to both sides. So we want to manipulate the left-hand side, and in doing so, start to change the right-hand side. All right, from here, you can do 3 times row 1 plus row 2 is going to give us our new row 2. And R1 plus R3 is going to give us our new row 3. I'm going to kind of zip through a little bit of this since we've done it so many times already. But still carefully, because I am prone to mistakes. So the -9 plus 1 is going to be a -8. A 6 minus 3 is 3. 0, 1, 3 right here. Then so that's 1. All right, hopefully you can see how we've gotten this far already. Now looking at this, I am seeing that this will work, and it's technically right, but these numbers are not very pretty for a pivot, right? It's going to be a little bit difficult. So I'm going to rethink things, and I could just go back and cut this out, but I think it might be helpful to just kind of see like how you can kind of pause and take stock and move forward. I'm actually going to do something a little different for the first step. I have changed my mind about interchanging those rows. And I'm doing that because as I actually look at this originally first row, I'm seeing the only really thing I need to do is just flip the sign, right? So I'm going to go ahead and do that. Embracing my mistakes here. I'm going to say our first step is negative row 1. It's going to become our new row 1. And that should make things a little bit cleaner. All right, so from here, I will be able to pretty clearly clean out these two columns, or sorry, these two values. 3 times row 1 plus row 2. So go to row 2. And I'm going to say row 3 minus row 1. It's going to become row 3. Alright, row 1 is staying the same in practice. It's going to use it to change the rest. So if I do 3 times 1 is 3, that's going to give us our 0 there. This will stay a 1. And now we have a 0 here too. Wow, yeah, that is a lot easier than my original plan of attack. We have negative 3, 1, and 0. And then in this last row, this is going to become a 0, negative 3, and 1. Yep. 0 minus negative 1, that's going to be a positive 1. 0 and 1. Yeah, absolutely no shame if you need to go back and kind of tweak your plans, because sometimes that is just the easiest way forward. So now from here, all I really need to do is get rid of that negative 3 and this 1 in the top, right? We'll do the negative 3 first. We can do that by doing 3 times row 2 plus row 3. It's going to give us our new row 3. Row 1 is going to stay the same for now until we come after that pesky 1 in the corner. Alright, that's going to become a 0. This is already a 0, so that's just 1. Negative 9 plus 1. Then 3 plus 0, doesn't matter, still 3. And that is going to give us 1 right here. Almost there, guys. We got to just clear this 1 out right here. And the way I'm going to do that is by taking row 1 minus row 3 as the new row 1. Alright, row 3 is going to stay the same. And row 1, this is going to give us the identity on the one side, which is exactly what we're looking for. Alright, I have negative 1 minus negative 8. It's going to give us 7. I have a 0 minus 3, is a negative 3. I have a 0 minus 1, is negative 1. Alright, so this is identity, which means this is going to be our A inverse. And again, remember, we can always check that by multiplying it by the original A. But I'm going to be a risk taker today, mainly because I'm a little bit tired. We'll see if that risk pays off. But I encourage you to try to do that on your own if you feel like it's good practice, which it is. Okay, so now that I have A inverse, I can remind myself that x equals A inverse times B, right? So, if we look back up here, that was so long ago, B is negative 1, 1, and 1. So, we could just multiply this, right? So -7 minus 3 minus 1 is going to give us a -11. We have a positive 3 plus 1 plus 0 is 4. And then I have an 8 plus 3 plus 1 should give us 12. Perfect. All right, now I believe this is right, but what we can do if we want to make dang sure, you remember that this comes from a system of equations, right? So we can go back at our original problem and just plug in all of this for the variables to double check. We're going to do that. Why not? I'm just going to rewrite the system down so that it is visible and I don't need to reflect upon my mistakes with all that red pen. All right, so this tells us, maybe it's good to reflect on like what this means too. This means that x is going to be -11, y is going to be 4, and z is going to be 12, right? So -11 minus 12, does that equal 1? No, -1? It certainly does. We have a -3 times -11 plus 4 minus 3 times 12 is 1. It's going to be 33 plus 4, which is 37, minus 36 is certainly 1. And then finally, we have a -11 minus 3 times 4 plus 2 times 12. What do we got? We have a -11 minus 12 plus 24 should give us 24 minus 23, which is 1, and that works. Look at that. All right, love it. We can self-check. Perfect. So this should give you an idea of like how to break down a system of linear equations into a matrix equation and solve from there. If you need a refresher on things like reduced row echelon form or identity matrices, we do have videos of that posted as well. And we also have a bunch of really helpful videos for all sorts of STEM lectures, other branches of math. We have engineering, some sort of technology as you would need. So if you're struggling in any of those classes, feel free to check out our channel. Please like and subscribe. And we will be back next time to talk about section 1.6. In the meantime, I hope you enjoy your day. Have a good one.